Hi, welcome to the 10th live session of Anthropological Appraisal course. So today we first go with the assignments, objective and subjective assignments along with detailed solution. Okay. And if time permits, then we'll go with the next assignment. Okay. So first let's today start with assignment 4, objective assignment 4. Okay. So first question is the following. Sorry, find it. Okay. So the first question is the following. That which of the following functions are equicontinuous from R to R? First option, when all those collection of families Fn where each Fn R to R given by x goes to x to the power n for all x. Option 2, all those family of functions so that each Fn the map from R to R by x goes to sin. Option 3, all those functions such that Fn R2 are given by Fn x is equal to x by n for all x belongs to all those functions Fn such that Fn R2 are given by Fn x is equal to x square by n for all x belongs to R. Okay. So for this we need to check which one of these are equicontinuous. And what is the definition of equicontinuity? The definition of equicontinuity is as follows. Suppose we have a collection f alpha. Okay. Then this is said to be continuous if for any epsilon greater than 0 and for any xy belongs to a domain here this is delta greater than 0 such that mod fx minus fy less than, I mean, let's call this collection small a capital epsilon for all xy with mod xy with delta. Basically here mod we should replace by metric space for internal situation, but anyway that's for the only basic purpose. So okay, so using this definition, which is or are the equicontinuous functions? How to derive that? So so first let's recall some properties. So equicontinuous is uniformly continuous. That's quite obvious, right? So equicontinuous means uniformly continuous. So let's say so first, I mean, uh, in order to remove some options, we need to first observe that which one of the following, which are the function which is not uniformly continuous. Okay, now observe that in option 1 and option 4, these are not uniformly continuous functions. Option 1 and option 4 are not uniformly continuous functions. So these option 1 and 2 are rejected at the first place. So we have option 2 and option 3. Okay, because in option 1 option 2 not all functions are equicontinuous. Not all functions uniformly continuous. Okay, so these two options are rejected. Okay, so now um, we need to consider on the option 2 and option 3. Okay, now the point is that now the point is that mm, consider option B. No, now in this option B, if we take any delta greater than 0, then we will get sum n such that fn 0 comma delta is nothing but sin x, or x belongs to open 0 comma n delta, which is equal to -1 or +1. Okay, so sorry, it should be maximum. So option B also rejected. So only a possible left option C. Now let's prove that the option C, that is the functions given by x goes to x by n, n belongs to natural. This collection of functions this form, I mean this family of functions form a equicontinuous family. So what to do? Take epsilon greater than 0. What do you need? There exists a delta greater than 0 such that what do you need to have? X by n minus y by n, this less than epsilon for all n belongs to n. Okay. Now what? Choose a n. We can take a small n belongs to n. Okay. And now delta to be less than delta less than epsilon by mod x naught minus for a particular mod x naught and y naught. So in that case, in that case, gfn x minus y less than epsilon for all xy belong. For all xy with mod x minus y less than delta. Okay, that's all it is. Now, okay. So, what are the correct final options? Option 1 already rejected because some fn's are not uniform continuous. Option 4 already rejected due to same reason. Option 3 rejected by some another argument, namely for for any delta greater than 0, you will get some n, so the fn 0 delta is equal to minus 1 plus 1. Okay. And finally, we have shown that option 4, option 3 functions are uniformly continuous. Okay, so that's all. So this is the first question. So now let's go to the third question. In which of the following three spaces boundedness is equivalent to totally bounded? Finite dimensional nominal space, option 2. Any nominal space, option 3. Locally compact metric space, option 4. Sigma compact metric space. Okay, just continue. Yeah. So what are the options? So bounded is my total bounded in which are the following metrics. So one is finite dimensional normal space, another is any normal space, third one is locally compact matrix, and fourth is sigma compact matrix. So now the question is the following: what does it mean totally boundedness? Okay, for sake of recall, let me tell the definition of totally boundedness. So let epsilon greater than 0 and x d be a metric space. It is said to be totally bounded if there exists finite family x1 x2 xn belongs to x, such that x subset of union v xi comma epsilon I is equal to 1 to x. That is, the x can be covered by ball of radius epsilon around those points x1 x2 dot dot. Then x is to be totally bounded. And in general, bounded does not mean totally bounded. Now the question is, in which of the following situation this is the case? that both are stable. So first of all, there is one option, finite dimension normal space. Okay. First of all, observe one thing, that any finite dimension normal space can be thought as finite dimension Euclidean space, namely R to the power n, right? Now observe that in R to the power n, boundedness, total boundedness, everything same thing. So that's a possible case that in finite dimension space, boundedness equal to total boundedness. But how to prove this? Okay, well, observe one thing, that um, in totally, I mean, yeah, observe one thing, that finite dimensional nominal space is isomorphic. I mean, yeah, homeomorphic with R to the power n. And in R to the power n, it's a basic linear algebra fact. And any R to the power n in R to the power boundedness, total boundedness, same. Okay. Now option 2 is any nominal space. So option 1 is correct. Now the option 2 is any nominal space cannot be. I mean, if you consider infinite dimension, it can't be R to the power something, right? So I mean, the possible case was that in any nominal space, I mean, infinite nominal space, the total boundaries may not same as boundedness. So for that, consider the following space, namely L2. That is all those sequences AI are the summation AI squared finite. Okay. Now consider the set A is equal to En, which is sum of L2. Then the set capital A is bounded as norm of each AI is equal to 1. But it is not totally bounded. Right? Because if we take any epsilon greater than 0, I mean, so if we take 2, if we take half, which is nothing greater than 0, and then observe that ei plus 1 does not belongs to b epsilon half. So this means what? This means A is not a subset of union of b ei comma half for some I is equal to 1 to m. Okay, because ei plus 1 does not belong, they're both. So that's why this space can't be totally bounded. Okay. So option 2 is not true. There is another option, locally compact matrix space. What does it mean locally compactness? Locally compact means any open cover contains a compact, sorry, any open never contains a compact subset. Now, so what about locally compact matrix space? Consider x equal to n, with a discrete matrix. Okay, so it is bounded, obviously, as x can be written as b small n comma 2, but not totally bounded. Why? As not totally bounded. Why? As I mean, if b n comma half is contains small n, so basically n cannot be written as finite union of b n comma half. So that's why x equal to n is a discriminatory, can't be totally bounded. Okay, so there is another option. What about sigma component matrix space? So okay, so option 3 left. I mean option 3 not possible. So what about sigma component matrix spaces? So for sigma component matrix space, taken with the discriminatory, and the similar argument will work. I mean, it is two similar argument, and also it uses some property of semi compactness, which is almost obvious. So I'm leaving it to the learners. If you have any issue with understanding of this sigma complementary spaces, totally bounded, industrially bounded, please ask me in the next live session. Okay. Okay. So let's go with the next problem. wait. Right. Okay. So next problem is as follows. Okay. So the next problem is the following. Which of the following are preserved under taking continuous image? This is the question. Which of the following are preserved under continuous? So you know the um, under continuous image, under continuous function, compact set goes to compact set, connected set goes to connected set, but what about the other properties like local, like what about local compactness? What about countable compactness? What about limit point compactness? What about sequential compactness? So, what about this? So, okay. So first, go with the first option, that local compactness. What does it mean? It means that if you take a point, if you take an open set, then it contains a compact surface containing that point. Right now, the point is that, I mean, suppose X belongs to a subset. Now the problem is that it is a compact subset, but if of you may not be compact, right? So if of you may not be open. So that's why, I mean, open neighborhood of, I mean, that's why continuous may compact may not be compact due to the openness condition. So what to do? So how to prove that? So so we have done one problem possibly 1 month ago, that Q with usual metric is not locally compact. Okay. Q user metric is not locally compact. We have done it before. Okay. Okay, so yeah, I think it's better to recall this argument first. So take any rational number R. Okay, belongs to some open neighborhood AB, which is of K compact space. Now take C belongs to open AB section Q complement. So there is sequence extended by density open AB such that and intersection Q such that this equal to equal. This implies what? This implies K belongs to Q. Okay. So but that's a contradiction because K is contained inside Q. That's why Q user metric is not locally compact. Now Q with a discrete metric to Q with usual metric is continuous, but image and map is identity map, okay, because let's say discrete metric, but image is not locally compact. So first option is out, correct. What about countable compact? That's what if any open cover has a countable support, that is, yeah. So now I mean, yeah, countable compactness is true. What about countable compact? What about countable? So let X be countable, let X be countable compact, and X we need to check the countable compact, right? So take any open neighborhood, take any open cover X is equal to union alpha. Then X equal to what? Union alpha if inverse to the open. Now X is a countable compact is equal to what? X is equal to union F inverse Y. I is equal to 150. This implies what? Fx is equal to union I is equal to 150 Y. So this implies Fx is countable compact. So if this proof is same as the proof of continuous image compact, the proof goes along the same line. Okay, there is nothing new here. So countable compactness if image preserved or continuous map. So what about option 3, option 4? Option, it's all about limited compactness, right? So limited compact means what? Any infinite set has a limit point. That is, yeah, any infinite set has a limit point. Okay. So what the argument is? So first of all, So, so let's try to prove this. If it and let's see whether the proof starts anywhere or not. Okay. So let if x to a continuous and x is limit and constant. You need to check what about fx. Okay. So means any yeah. So what to do? So choose the infinite subset x and n belongs to n of fx and choose this subset to be infinite. Now let x n belongs to x. Does that if x n equal to y. Because we're in the image of it. Okay. So so then we have some x n subset of x and the infinite set. Now since x is limit point compact, so this set has a limit point. Call it x. Now now it's a natural claim that if x will be a limit point of z y. So for that what we need to do, we need to show that if we take any point, sorry, any open set u containing fx, u contain at least y and not for some n naught, right? Now for that what you need to do, use an open set containing fx is what x belongs to f inverse u and f inverse u is open set f is continuous. So this implies what, some x n naught belongs to f inverse u. This implies what, this implies y n naught belongs to u. So that's why u is the limit point of the set small. So if it's the limit of the set containing those y's. So that's why. So this does what, this tells the set that the space capital Y is limit point compact. So option true, option 3 is also. What about option 4? Option 4 is all about sequential compact. Then that is any sequence has convergence of sequential. Okay. So let's try to do it. Let yn be a sequence of fx. So corresponding fx, then we will get here be a sequence x and be a sequence in x, that f of x n is equal to y. Okay. Now since x is sequentially compact, this implies this sequence x n has convergent subsequence. Let it be x and here. And then obviously and let x and k goes to some x naught. So obviously f of x n goes to f of x naught, and this is f of x naught and nothing but something y and k. So y and k is subsequent of y minus some point. So that's why the sequential compactness is also been preserved under the continuity. So what is it? Okay, let's wait. So the sequential controls this period. So so let me repeat this whole arguments of this question because I feel that the question is not that much direct. Okay, so can you wait? I have to get back after some minutes. Okay. So let's okay. So let me give the argument for this question. I think it's good to start with this first. Okay. So so the question is that which of the following are preserved and continuous image, right? So for that, what we can do? So there are four options: local compactness, countable compactness, unit compactness, sequential compactness. So first go with the local compactness. Okay. So recall the definition of local compactness. Recall the definition of local compactness. Okay. So this means what? This means if we take any point and open set containing that point, we'll get a compact neighborhood containing that point. Okay. But the problem is here that suppose the x belongs to k subset of u, but it does not mean that f of u is open. F of k compact, that's fine, but f of may not be open. So that's why if you take any function which is not an open map, compactness need not be preserved. Okay. So that's why if now one example of space which is not a locally compact is the Q with the usual metric. The proof has been discussed all that 1 month ago, and today also here we have seen the proof. Okay, so let's not get in the proof of the not locally compactness of Q usual metric. So now consider Q discrete metric to Q usual metric, consider identity metric. It's obviously continuous, but f of Q is equal to Q, which is usual metric, so it's not locally compact. So option one is rejected. What about option two? Countable compact. Countable compact means any open cover is a countable subcover. This means this is a countable compactness. We have seen that if we take any open cover fx equal to union u alpha, then x can be written as union alpha f inverse u alpha. Now x is countable compact, so x can be written as union I equal to 1 to alpha f inverse ui, and fx is equal to union I equal to 1 to ui. Fx is countable compact. And this proof is same as a compactness, I mean continuous image of compact to compact, the proof is same. Now there is something called limited compactness. Okay, this is what let f of x to y be continuous function, x is limit one compact. Then what about fx? Okay. So consider the sequence yn, n belongs to n. So limit compact, any infinite set has a limit point. So we are taking an infinite set of yn in fx. Since this set small yn is in fx, so we will get as infinite set of xn in x as f of xn is equal to yn. Now since xn is locally compact, so this x sorry limit point compact, so this xn has a this set xn has a limit point, call it small x. Now we are claiming that this fx is a limit point of y. This means what? I mean, this means what we need to do. If we take an open set u and any um, if we take any open set u containing the point small fx, then we need to show that u contains some point other than small y. Okay. Now, since there is open set containing fx, so x is contained inside the open set x inverse c. Now, since x is the limit point of the set xn, x belongs to u, so xn belongs to, I mean, so that if inverse u contains some point of y for some arbitrary y naught, so this implies what? This implies f of xn naught belongs to U. This is like Y and not belongs to. So that's why Y is not compact. Okay, so the argument. So linear compactness is on continuity. Now there is last option, which was the sequential compactness. Is it preserved or not? Sequential compactness is what? Any sequence has a convergence of sequence, right? This is what we need to check. Yeah. So if you take an extended sequence, so it must be so they I mean though y is equal to f of x, so that x and forms a sequence in x. But since x is sequentially compact, this x and sequence has convergence of sequence. Call it x and k, and let x and k goes to some point x and naught. So this means what if x of n k goes to f of x naught. This implies y and k goes to f of x and naught. So that is the contradiction. I mean, sorry, this is not contradiction. This is the sequence y and k has a limit point f of x naught. That's all. Okay. Okay. So okay, so that's all for this question. Now let's go with the next problem. The problem is given as follows. So with four statements, the first one is every non-empty subspace of Rn locally compact and Hausdorff. Option 2, if X is a non-empty subspace of Rn, then the one point compactification X is Hausdorff. Option 3, I mean, yeah, that's all. Now, then, which of the following is true? Then, which of the following article. So this is the question. So okay. So which is the following? So first option is what non-empty sources are in is locally compact house. Second one, if X is non-empty subset of Rn, then a one-word computation of its house drop. So this is the first one. So uh, one second. One second. Yeah, okay. So first of all, okay. So let's look at the question now. Sorry for the unconnection in between. So it's written every non-empty sources are in locally compact house drop. Okay. So in Rn, any source with house drop, but any source with cannot be locally compact considered Q. So Rn equal to 1. So option 1 is invalid. So option 1 invalid because Q locally compact. Q is not locally compact. So option 1, no. What about option 2? If X is non-empty sub to Rn, then the one with computation is held. Option 2 is not invalid. Option 2 is also invalid. Take X3, we are choosing X given in the answer 0 infinity cross Rn. R. It has also R2. Anyway, no need to consider this. And I mean, take x equal to 0, comma the point 0, comma 0 union 0 infinity cross R subset of R2. This is not a local compact house drop, so it's one by compactification of the house drop. Okay, so that's why both option 1 and 2 both are incorrect. Okay, so so that's all for the objective questions. So now let's go with the subjective. Sorry. Now let's go to subjective assignment. Right, let me open the subjective assignment first. So once page. So okay. So assignment 4 surgical question. So let's take start with questions. So first question is that show that a sequentially compact one space is boundary compact. Because you compact even as a countable compact. So this is what it means. So first let us recall what does it mean as sequentially compact. So sequentially compact means any sequence a convergent subsequence, and countable compact means any open cover as a countable subcover. Anyway, in matrices everything is same, but in random topological space these are not same. So the sequential compact, which is a T1, means if you take any two point, there is open set containing one, not containing another. This is T1 space. So if we sequentially T1 space is countable compact. So what to do? Let even be countable now. If so, suppose it has no counter. Suppose if it has no countable, by the way, I think I should mention one thing in this batch. Um, we have discussed the assignment 4 in last class, but actually it asked me to uh, go with the arguments once again. So that's why I am going through this solution for the assignment 4 once again. Okay. So now assume that it has no countable subcover. So if it has no countable subcover, then we can choose xn belongs to x minus union of uk is equal to 1 to okay. And then the set xn is infinite. Now since x is sequentially compact, so the sequence xn converges in x to small x, okay. X belongs to un for some. Now since x is a T1 space, so it follows that un contains infinitely many elements of xn. So I mean, but what do you know? But none of x k greater than n are in UK. So which is the contradiction? So that is the argument. So what is the argument? Let me repeat the argument. Yeah, because it is quite tricky. So first, to assume that it has no countable subcover. So we are taking any open cover UN and assuming it has no countable subcover. Then we are choosing some small xn inside x minus union x where xn is finite. Now since x is sequentially compact, so the sequence x converges in x to small x for some small x. Okay. So obviously small x belongs to some UN. Okay. Now since x is a T1 space, so it's a fact that UN contains infinite many elements of x, but none of the but by the construction none of the x k for k greater than n are in UN. So that is a contradiction. Okay. So let's go to problem. Let f x2r be continuous real valued function where x is countably compact. Then show that f is bounded and attains. So the question, if x2r is a continuous regular function, then show that it is bounded and attains the extreme. It is bounded continuous function. So, sorry. So the question is as follows: suppose if x2r be contains real function, so that it is bounded at its and x is counted compact, it is bounded, so that it is bounded at its extreme. So basically, it is we have seen one theorem that if a function is from compact with x orbit to space, then the function attains its extreme. Now, actually, this condition can be weakened by saying that x is counted compact. Anyway, it's a very nice result. So let's prove it. So what to do? Let's go with the normal direction. Just so okay. So from the quiz questions, I mean from the MCQ type questions, we got to know that since x is countably compact, so if x is also countably compact, okay. We have already done this in the MCQs. And also do note f of x subset r. And if it countably compact, this implies fx is compact. So by Heine-Borel theorem, fx is closed and bounded by Heine-Borel theorem. So this tells it is bounded and attains its extreme. So this is the argument. Okay. Basically, this is nothing different from compactness case 4. If x is countably compact, okay, so it is compact. Any compaction is close bounded, and it contains its both supplementary. That's all. Nothing real. There is really nothing much. Okay. So let X be a metric space. Show that for each r greater than 0, here as of year of which is maximum with respect to the property that any 2 point x not equal to y to year y further if x is limit point compact then show any set here is finite. So how to approach this problem? So so here the set capital A has a property and which is matched with respect to some given property. Okay? What? So for that, consider the collection CR. All the subset of P such that PH is greater than R for all x not equal to y inside that. Clearly this CR is in written subsets of x here in CR. Now we are giving this a partial order and basically we are trying to use poset and then try to use Johnson. Okay, so we are doing partial order in obvious way, that is by inclusion, and so this says that this set CR must be finite. And so now let's be point compact. Now if some r greater than 0, you are finite, then there exists a sequence of distinct terms xn in here which is not convergent as for any n not equal to n. And so we have with the R. Okay. I mean, it's a quite tricky technique. It's quite tricky. Basically, let so let me do that. We are choosing some set capitals here. Okay. Now it is non-empty, and then we are giving a partial order in obvious way by inclusion, and by simple John's limit, we are smart with finite. Now X linear compact, so it's for sum of R. We have a sequence of distinct terms xn in AR, which is not convergent. As for any n, we have xn, dxn, omega xn. Okay, that's all. So now, yeah, it's a quite tricky problem. You should think about. You should think and think about it. Not full time because it's a now. Okay, let me do the next problem. So the next question for me, show that every matrix space which is a limit point compact is separable and hence second count. Every matrix space which is really compact is separable and hence second count. So and conclude that every compact matrix space is second count. Second column is what? If we open second column is it has a kind of basis for its topology. Okay. So what to do? So, okay, what is the question? What is the information? F is a limit point compact. So let X be a limit point compact. So X is compact. Okay. And so it is complete and totally bounded. That's very good. For each n belongs to a, we are define the set Sn to become xn1, xn2, xn, okay. So that x is equal to union of E1 by n, xni. Now the claim is that S equal to union Sn, and also the countable set is dense. And what to do? So for that, in order to see what it is, so take x belongs to it and epsilon get choose n belongs to it. N belongs to n such that epsilon less than 1 by affinity property. So then there is xn I for some I belongs to 1 for 10 or 1 will got crashed. Sorry, just a minute. Let's open the 1. Okay. So it's a countable set claiming that it is a dense set. Okay. To see this, what we'll do, take any x belongs to x and choose the epsilon greater than. Choose n belongs to n so that x epsilon less than 1 by affinity probability. So now take xni for some I belongs to 1 to kn so that x belongs to v1 by n xni. Okay. Now since that's all, I mean, yeah. So this means what? So what we need to do? We need to do that every compact material we need to compact separately. Means it's countable dense subset and semi-countable. So this is our the step capital which is pence, and so that's why the same algorithm goes and it should the same transfer. Okay. So what we have done. So it's a linear compact. So there is compact. So it's complete total bound of what is called a factorization. We are choosing for each n we are choosing a small n and corresponding to Sn equal to so xn to total xn. Yes, other x equal to union I equal to 1 to b 1 by n. Now we are claiming that S the set S equal to union addition tens. So what we look for any x belongs to between epsilon, so the epsilon is 1 by n, and this happens due to our property. And then we are getting from some xi, xni, so that x belongs to b1 by n. So this implies any open set for U intersection gives us knowledge. That's all. Just there is another question that show that a totally rounded metric space is separable and so basically this is what in it says that in metric space totally roundedness, separability, self-contability are all same. So okay. So for the so for the argument this argument is same as the previous question almost same. So let me go with the line let me go with the arguments associate. So for each n, it considers a small n is equal to xn1 x into dot order x and n. Okay, so that x equal to union b x 1 by x and I is equal to 1 to k. Now think about why such a thing will happen, because it's a totally bounded as totally boundedness of the set factor x. Now the thing is, we claim that this set x is equal to union s1 is 10 sin x. For further, what we will do, take x belongs to x and epsilon greater than 0, we too can get small n belongs to n such that epsilon greater than 1 by d to the Archimedes property, and then we say there exists x then I for some Archimedes equal to 1 to kn, so that x belongs to b1 by x and I, that is dx comma x and I less than 1 by n less than epsilon. And for second part, observe that the set b1 by n x, n belongs to n, x belongs to s, is countable set which is the basis of x. Think out of what is the basis. Okay, so basically same argument, we are for each and we're choosing such a capital Sn and that x equal to union of those elements around the open balls of radius 1 by small. This is totally boundedness, and now we are showing that this s is 10 in capital X. Then what is for each x belongs to capital X? Some epsilon greater than greater than 1 by some small n, so the epsilon greater than 1 by n. And then there is x and I such that for some I with I will 1 to k, I such that x belongs to 1 by n x and I. So that this dx I less than 1 by less than epsilon. Okay, so that's why that's the capital X is dense, and that's our denseness. And that's set b1 by n x, n belongs to natural number, x belongs to set in the chosen dense set S is a countable dense countable set which is the basis of it. Now what is the basis? By choice of construction it's the basis. Okay, so that's all it is. So now okay, so now let's go with let's go to the next assignment. Wait a minute. Oh, oh. So let's go with the assignment problems. MCQs. And first is the true or false. You have a house of 1 point property. It's true or false. So first try to think how to attack the problem. Hmm. So there is a fact or theorem that space space H is locally compact across if and only if it has uh, 1 point Hausdorff H. So due to this theorem, if Q has a 1 point Hausdorff computation, it should be compact, right? I mean, it should be locally compact, but Q is not locally compact. We've already seen the previous MCQ or in one that we have already seen. Q with usual topology is not locally compact. So that's why it's a false. One question to is homeomorphic compactification. This is what? Equivalent means what? That is equal to compactification, then homeomorphic, then the restriction uh, we think about what does it mean by equivalence. So it can be let us think about it right. Okay. I don't know what I couldn't understand how you think about it and tell answer in the next live session. I don't know what does it mean by equivalent. So, so let's go to the next problem. That is the number of closed subalgebras of R3. One dimension. Option 1. Think about it, isolate values. So how so the number of closed subalgebra are three that are the one-dimensional subspaces is what. So how to approach this problem? So first look at the what are the one second. So first we need to understand what are the one-dimensional closed subspaces. So let W be one-dimensional closed subalgebra. Sorry, it's not subalgebra. And let the point ABC is its base. Then ABC whole square. By definition of algebra, it is A square B square. So for some lambda belongs to R, we have A square B square C square is equal to lambda A. And this is what A square lambda A B square C square lambda. Now as W is one dimensional, so and not all ABC non-zero, so the following cases will occur: A equal to 0, B equal to 0, C not equal to 0. And this case is generated by 0, 0, 1. Option 2 possibilities: A equal to 0, B not equal to 0, C equal to 0. It is generated by 0, 1, 0. Option 3: A not equal to 0, B equal to 0, C. It is generated by 1, 0, 0. Option 4: A equal to 0, B not equal to 0, C. In this case, generated by B equal to C equal to lambda. And hence we get the subalgebra 0, 1, 1. And similarly, there are other subalgebras: A not equal to 0, B equal to 0, C not. We get A equal to C equal to lambda. And the subalgebra generated by 1, 0, 1. A not equal to 0, B not equal to 0, C equal to 0. In this case, subalgebra generated by A equal to B equal to lambda, and is generated by 1, 1. A not equal to 0, B not equal to 0, C not equal to subalgebra generated by 1, 1, 1. So that's all. So basically, what we have. So basically, what is the argument here? So since algebra, so we are choosing some point A, B, C. So that's why only there are 7 cases, right? So the correct option is 7. So basically, what we have done. So we choose a point A, B, C, and we due to Savalier property ABC whole square equal to A square B square C square. Now since it is a one-dimensional space, so since it's a one-dimensional space, so ABC whole square equal, so I mean A square B square C square lambda and ABC. Now A square equal lambda B square lambda is A square lambda, and that will be a one-dimensional space ABC not equal. So A equal to 0, B equal to 0, C equal, I mean there are total 7 cases, and each of this is a generator 001, 010, and so on. So that's why there is total 7 possibilities of one dimensional algebra. So that's why the answer is given. Okay. Yeah, it's a quite new problem, but basically here what we actually use the ABC whole square equal to ABC equal to A square B square. So this is the one thing we have used, and there are only one another thing is that is a one dimensional. So A square B square C square is the lambda of ABC, and since ABC are not all zero, so ABC is actually we can consider the base element of the W. So that's why A square B square C square lambda ABC makes sense, and then from that we are getting the whole result. Okay, that's the argument. Okay, so that's all for today. Thanks for attending this session. Uh, Today I'm now going to end this session here. If you have any doubt or any issue, you can ask me in the next live session, or you can email me. I will reply over the session. Okay. Thanks. And disconnect the call.